We're having a look at the electrolytic cell. The electrolytic cell is an example of where we have a non-spontaneous redox reaction occur, which means that we need to add electrical energy that will be converted to chemical energy in our redox reaction. So when we add the power source, we have our two electrodes here that we are going to suspend in a solution. And the example that I'm going to use today is when we have a solution of copper sulfate. So copper sulfate AQ, remember that is Cu2 plus ions, SO4 2 minus ions that are surrounded by water molecules. Remember also that the water in a smaller amount will form ions H plus as well as OH minus. If we look at our electrolytic cell, if we look at our electrodes, we know that we will have our anode and our cathode. Our anode is where oxidation will occur, and our cathode is where reduction will occur. We also know that our anions will move to the anode. In this example, our anode's going to have sulfate and hydroxide ions moving towards it. So here we will have competing of SO4 2 minus and OH minus at the anode to go through oxidation, which is the release of electrons, and at the cathode we will have Cu2 plus and H plus cations that will compete to go through reduction. So when we go and look at these ions, we can go and identify our half reactions. For copper, Cu2 plus 2 electrons will form Cu, and here our reduction potential has a value of 0.34 volt. Then if we go and look at hydrogen, this is going to be our half reaction for hydrogen. 2H2O plus 2 electrons will form H2 plus 2OH minus. It has a value of negative 0.83 volts. When we have a look at these two half reactions, remember that H2O is now actually H plus and OH minus. We see that the H plus becomes H2. And if you look at these two values, we can clearly see that the copper ions has a higher reduction potential than the hydrogen ions, which means that at our cathode, the copper ions will go through reduction. We also know that our copper ions are therefore stronger oxidizing agents than our hydrogen ions. And we see that this half reaction is what will happen. Our hydrogen ions therefore are not going to go through the process of reduction. When we go and have a look at our half reactions for the sulfate, SO4 2 minus plus 4H plus 2 electrons will form SO2 plus 2H2O. It has a cell potential value of plus 0.17 volt. And then if we go and look at our other half reaction here, we have O2 plus 4H plus 4 electrons forming 2H2O. So as we can see here on the right hand side, we have our OH minus becoming O2. And now if we have to go and choose between these two, I'm also going to add in the value for this half reaction plus 1.23 volt. Remember that if we read this reaction from the right hand side, this plus 1.23 now becomes negative 1.23 volt. So if we have to go and compare between SO42 minus with a value of plus 0.17 and the second half reaction here where we have hydroxide becoming O2, we can clearly see that our OH minus is a much stronger reducing agent, and it will therefore go through the process of oxidation. So we see that OH minus will form O2 gas. Remember that this is now going to happen at our anode, so we will see oxygen bubbles form that will be released. At our cathode, we will see a copper residue form on this cathode. We therefore see that our SO42 minus is our ion that will not react, and we end up having H plus ions and SO42 minus ions in solution that will not react, and this forms H2SO4. I am using table 4A here, where fluorine is used at the top and lithium at the bottom of the table of standard reduction potentials. On the left-hand side of your table, you will see an increasing ability to oxidize as we move from the bottom to the top, and at the right-hand side, from top to bottom, an increasing ability to reduce. It's very important that you go and practice problems, and remember, if you have any suggestions of any electrolytic cells that you are struggling with, drop a comment so that I can go and perhaps also do a video on that specific example.